Hello students, today's class you're going to see about the Airwedge experiment. The objective of this experiment is to determine the thickness of the given wire. Now let's see what are the components required to do this experiment. Alright, let's see what is an Airwedge, how it is formed. Now you can see in this view there are two parallel glass plates. They are tied with the rubber band, and in between a wire is inserted. You can see here in this point. So in between the two glass plates a wire is inserted. So from this point to this point the wedge is formed between the two glass plates. So where air is occupying, so that forms as an air wedge. So using this air wedge we are going to form the interference pattern. So the interference pattern formed will be like a formation of fringes. You can see, if you see in the microscope, this is going to be the pattern. Alternate bright and dark fringes are seen. To form the fringes we need to have a glass plate which is exactly inclined at 45 degree as you are seeing now. This is the glass plate we are going to use, which is fit in a stand, but the glass is inclined at 45 degree. So we are going to place the glass plates in this gap. I'll show you how to place. Alright, now we can see the setup of this Airwedge apparatus in the microscope. You can see the inclined glass plate G and the Airwedge glass plates which are arranged this way, and there is a source, sodium vapor lamp, and the light is allowed to fall to the gap of the glass plates, that is Airwedge, and the microscope is vertically arranged to view the pattern which is formed in the Airwedge. So now you can see the stem of the microscope is placed vertically to view the pattern which I have shown. Actually the fringes are formed in this area. You can see here in this area the fringes are formed in the gap between the glass plates, but you are viewing through the microscope. So inside the microscope view you will get the fringes pattern which I have shown earlier. And now how to get the clear pattern. For example, you have a screw here. If you try to adjust the screw, you can have the clarity. If the lighting inside the view is not proper, you can move the microscope in such a way the light can enter into the wedge clearly. Now you can record the readings. You are going to focus any one of the fringe as N. That can be made to coincide with the crosswire of the microscope, and then you will make a note of the reading. There are two scales in the microscope. You can see this is a vertical scale and this is a horizontal scale. So we are going to take reading of this horizontal scale. So how to take the readings in the microscope we will see now. Alright, you can see, for example, if you are taking the reading in this horizontal scale, you can see there is a 0, and this is the main scale. This is the main scale, this is the vernier scale, and there is a 0 in the vernier scale, and the vernier scale is divided into 50 divisions, and the minimum reading of the main scale is 0.05 millimeter. You can see 1 centimeter is divided into 20 divisions. So the minimum reading in this main scale is 0.05 millimeter. So that only divided into 50 divisions in this vernier scale. So the main scale reading can be taken by taking the coincidence of the 0 of the vernier scale with the main scale. For example, in this case it is almost like 2.1. Alright, you can see now it is 2.10. So this is the main scale reading. Now out of the 50 divisions in the vernier, any one of the division will coincide with the main scales, any one of the reading that should be taken. May not be focused with this camera, but you can understand any one of the vernier will coincide with the main scales reading. So the reading in the vernier should be taken as the vernier scale reading. So we have two readings now. One is the 0 of the vernier coincides with the main scale. That reading should be taken as main scale reading. And out of these 50 divisions in the vernier, one of the division is going to coincide with any one of the reading in the main scale. So the reading of the vernier, which is coinciding with the main scale reading, should be taken as vernier scale reading. For example, if the microscope is used to take this reading, then the LC of the microscope is 0.001 centimeter. If you take the reading of the main scale as 2.1 centimeter, vernier scale coincidence as 35, and vernier scale reading will be this 35 should be multiplied with LC, that is 0.001, so you'll have 0.035. Now the total reading can be taken as 2.1, that's the main scale reading, plus vernier scale reading 0.035. So if you add these two, you will get 2.135 centimeter. This is going to be the reading of the microscope for the focused fringe. So likewise, the experiment can be taken for the first we have recorded the reading for the nth fringe. Any one of the fringe can be taken as n. Now you will move the microscope screw for fine adjustment. You will move the 5 fringes, and now the crosswire is focused with the 5th fringe from n. So that is n plus 5. So you can record the reading now as we have understood. Similarly, you will go with the next 5th fringe. So it will be n plus 10. Likewise, n plus 15. You will go up to n plus 50. You will record the reading for all the 50 fringes with a gap of 5 fringes as we have seen in this. So microscope reading is recorded. You can have the width of 5 bands by subtracting the reading of the n plus 10 with n plus 5. Likewise, every 5 difference is there, you can take this reading width of 5 bands. And if you divide this reading with 5, you will get the bandwidth that we can use it in the calculation. To find the thickness of the given wire, we need to have the formula as L lambda divided by 2 beta, where lambda is the wavelength of the light used. Here we are using the sodium vapor lamp. The wavelength of yellow line should be used. And L, we shall see now how to. Now the microscope is adjusted to focus the rubber band in the view. Now the reading is taken as L1. Similarly, the microscope is moved, and the wire in between the two glass plates, it is seen as black here. So in the microscope you can focus this one. So you will have the second reading L2. Now the gap, the difference between L1 and L2 in the microscope readings will give you. Now using the bandwidth beta we have calculated from this tabulation, and then length now we have understood from L1 and L2 reading, and lambda, that is wavelength of the sodium vapor lamp, that is the yellow line. Now you can calculate the thickness of the given wire using this formula, and you can display the result, that is thickness of the wire in terms of 10 to the power minus whatever the answer comes in terms of meters. Alright, how to take the reading in the microscope, which I have explained. You can see the 0 of the vernier scale coincides with the 2.6 of the main scale. So the reading is 2.6 in the main scale. So the main scale reading goes 2.6, and out of all these 50 divisions, you have to look for which division is coinciding with the main scales, any one of the reading. So the reading of the vernier which is coinciding straight with the any one of the reading of the main scale should be taken as the vernier scale coincidence. From main scale reading and vernier scale coincidence, we can record the microscope reading. As you can see, the main scale reading is not 2.1, it is 2.6, and vernier scale coincidence is 35, and 35 should be multiplied with LC 0.001, so you get 0.035. So if you add the main scale reading 2.6 with vernier scale reading 0.035, so you will get the reading as 2.635.